Okay, welcome to the update from Science Pipelines. We've got a lot of talks throughout the meeting on Science Pipelines, but ever since the algorithms workshop, we've had a dedicated session during the PCW in order to update you on what we've been up to in the last year. The format is going to be a plenary length update on highlight reel from the last year, and then we will do a 30-minute fireside chat informal QA with the pipelines team, which is seated on the sides here. Robert is going to moderate the question and answer discussion. Ian Sullivan is moderating the virtual participants. He'll be monitoring both BlueJeans and Slack, unless Meredith, are you monitoring BlueJeans? Melissa, okay. We prefer that you send your questions on Slack. We will be monitoring the BlueJeans chat, but we absolutely will not be monitoring the hands up feature on BlueJeans. It's very hard to do with the very long participants list. Remember that we have a code of conduct. If anything happens, feel free to yell out code of conduct. If it hits you later, as it often does me, feel free to go seek out the person and talk to them later. And any of those people, Rand Paul, Andy Connolly, and Melissa are also, please talk to them if you would like as well. Ken Herner is taking notes, and I think everything else we have already covered. Okay, can everybody hear me okay before we get started? Awesome. Okay, my name is Yusra Al-Sayed. I manage projects for the Science Pipelines. I'm going to be speaking on behalf of the whole Science Pipelines team today. The first 30 minutes or so, I'm going to give an introduction to pipelines, how we monitor pipeline quality, and some new features that have happened this past year. Think of it as a scientific release notes. At the bottom of every slide, the scientist who led that project will be there. If you see the name formatted as first name, last name, that means that they're here in Dove Mountain and would welcome questions during coffee breaks. If they're listed as a Slack handle, that means that they're attending remotely and would prefer questions via Slack. After that, we'll be covering the topics that we covered at the algorithms workshop in a medium dive format. The plans that we described in the algorithms workshop are all still current. If you're curious about what the plans are, for example, for shear estimation, I welcome you to go watch those videos. Today we'll be giving you updates on a selection of these. You'll hear from Claire Saunders on astrometry, Fred Moolekamp on deblending, Ian Sullivan on image differencing, and plans for Real Bogus classification by Nima Sedaghat, and finally, Solar Sytem Object Linking by Ari Heinze. If Ari and Nima's names sound new, that's because they joined since the last PCW. Welcome, Ari and Nima. We've also had a few more people join this summer, Erfan Norbaksh, Aaron Howard, and Brianna Smart. Welcome. We held a boot camp in June, the first we had in a few years. If you are a power user or want to hear from Jim Bosch on Gen 3 Butler theory, I welcome you to go check out those videos to learn more. All the material has been refreshed since the last boot camp we had a few years ago. Okay, Science Pipelines. The Science Pipelines is the code base that takes the raw pixels coming off the telescope, combines them with reference catalogs, calibration data, and produces processed images and catalogs. While we expect you to be able to do a lot of your science with the catalogs, we know you will invent novel science that requires image processing. Therefore, the processed images are also a first-class data product. And these are the data products we expect you to use for your shift and stack algorithms to test your Planet 9 hypothesis or detect your ultra-diffuse galaxies. And in fact, I would see it a major success of Rubin if people are reprocessing the images 10, 20 years from now with novel image processing code. We do not expect you, however, to have to redo instrument signature removal. And when we have to make trade-offs, either due to developer time or computational resources, we will always prioritize the lower parts of the pipeline, the parts closest to the camera, like ISR, parts like coads and PSFs. So while we expect there to be additional shear estimation codes that are run, we are committed to having them be able to run on our coads and our PSFs. We will get these images to you images and catalogs to you in two ways, fast and slow. Fast via the prompt data products, the nightly alert stream. This is to support science that requires rapid follow-up. You'll hear me refer to this as AP throughout this talk. Slow are the annual data release products. These support static sky science and statistical studies of variability. This includes calibrated light curves, which are part of the data release products. When you hear me refer to DRP, this is the data release processing pipelines. We are 2 years away from operations, but we have prototype pipelines in place. However, we expect these to evolve over the next 2 years and the next 10 years. And this is because we are committed to not only meeting requirements, but providing state-of-the-art algorithms. And the state-of-the-art has evolved a lot in the last 10 years, and there's no reason to think that it won't evolve in the next 10 years as well. So how do we know these prototype pipelines are working if we don't have LSST CAM data yet? We use precursor data. We use a few wide field cameras and a new one. So we use DESC's DC2, which is useful for anything that requires truth match. But it doesn't have the gory realities that real data has, like ghosts and glints, cosmic rays. For those, we use DCAM and HSE. DCAM is useful because it does not have an atmospheric dispersion corrector, just like LSST won't. And hypersuprime CAM is deep as we're expecting from LSST. And the latest addition to our precursor data is Oxtel, and the Lattice instrument, which has a real LSST CAM chip on it, which makes it useful for testing instrument signature removal. We process these data sets of 3 sizes in subsets of 3 sizes at 3 different cadences. We process hundreds of square degrees on an annual cadence, tens of square degrees on a monthly cadence, and less than a square degree on a nightly cadence. The nightly reruns are done to keep the pipelines healthy. Every night, there's a nightly release of the pipelines. And as part of these pipelines, we run 2 Jenkins jobs that produce metrics that are dispatched to Squash, which is an instance of InfluxDB and has an interface that we call Chronograph. We look at four different dashboards on Chronograph, which have plots of scientific metrics and runtime metrics as a function of nightly release. So if somebody merges a new feature that makes alert production take twice as long, we will know. That real example. So for data release production pipelines, we run the RC2 subset. This is the exact same subset that you'll find on the Getting Started guide at pipelines.lsst.io. It's one patch and takes about 6 hours to run. For the alert production pipeline, we run AP Verify on a couple CCDs from HSE and DCAM. Monthly, we run approximately 10 square degrees, 5 every couple weeks. So this size, 5 square degrees, a few tracks, this is pretty much the bare minimum that you can use to test the robustness, speed, and performance of an algorithmic change. The scientific performance metrics that come out of this are much more robust and reliable and are used for characterization reports, for example. We look at both metrics and plots coming out of these reruns, and these are reruns that we run before merging major changes to check to make sure that the metrics haven't suffered. So for this, we use DCAM PI data set called HITS, an HSC subset called RC2. This is PDR1 depth, 3 tracks, 2 of them are wide, 1 of them is the ultra deep, which has tens of visits. We also use DC2, TestMed1. TestMed1 refers to 2 tracks, 3828, 3829, that are 1.5 year depth. And in the plots that you'll see later in this talk, you'll see them reference RC2 and TestMed1, and these are the subsets that they're referring to. So because we are testing pipeline quality, what we do is we hold the image data sets fixed and then vary the pipeline, and then you know that every change you see is a direct result of a pipeline change and not image changes. Annually, we run hundreds of square degrees as parts of external data releases and internal data releases. The HSC Subaru Strategic Program uses the Rubin LSST Science Pipelines as their data release pipelines. And this has been the most valuable source of feedback on pipelines quality so far. There's nothing better than scientists trying to write papers with your data products. We've released 3 public data releases so far and have just finalized the pipeline for the 4th one, PDR4. You'll hear me say PDR4 a lot in this talk. We are currently running a 100 square degree validation run because you'll see we made a lot of updates to the algorithms this past spring, and we'll know the results of that later this fall. We also released DP 0.2 based on DC2 data, but I think you've heard a lot about that already this meeting. I'll also say that this is very important for robustness because you won't find your 1 in a million error unless you process a million images. Okay, moving on to new features. First, we've invested a lot of time in tooling for monitoring pipeline quality. So this past year, after converting the packages that make plots and metrics with every that get executed during the pipelines from Gen 2 to Gen 3, we got to a steady state, took stock of where we were, and realized that a lot of the code that is used to generate the plots and the code that generally generates the metrics could be shared, more modular, and more reproducible. And this gave birth to a new package called Analysis Tools, which is a redesign of what was Faro and Analysis DRP. When I say shares more code is more modular, what I mean is that the metrics that are printed on the plots that automatically get generated during pipeline execution, like the little numbers in the bottom there, they match exactly what is loaded into Chronograph. And not only that, you can load up a notebook and get the exact same rows that went into this plot and went into the computation of the metric, and play around with it, explore it, make your own plot for a publication, or just answer some hypotheses that you have. We've also created a new dashboard based on matching DC2 outputs to truth catalogs. So this is useful for plotting completeness, purity, matches, recovery of positions, magnitudes as a function of pipeline version. And we have both a new dashboard in Chronograph and a new set of truth match plots. We are using Oxtel for validating calibration products and to prepare for commissioning. We've been commissioning the Sky transmission code, calibration products, and using this to build new tools. For example, Rubin TV, where you can view the all-sky camera observations every night and have a nice dashboard where you can view every image being taken with Oxtel Lattice and some QA plots of those images. Even though Lattice is tiny, it works very hard. We've been producing a 1 square degree survey of a field, one of the original Harvard Standard Region fields that were used to calibrate the southern sky. This image here is from Eric Dennehy, and it's a GRI COAD of more than 2,500 images taken this spring. We have a prototype of the prompt processing framework in operation in Google Cloud. This uses the pub/sub Google messaging framework to get a notification that a visit is ready. It prepares a pipeline, runs the pipeline. And next steps are to port this to port this to the USDF and be able to prompt process images coming directly off of Oxtel from Lattice. We've also, for the first time, stood up a production-like Kafka cluster and alert archive. We have all 7 community broker teams were able to successfully authenticate and receive sample alerts during a test run in January. Next steps on this is also to port it to the USDF. We also characterize the alert production runtime performance using IMSIM data. IMSIM data has the same geometry as LSST CAM and the same expected number counts, making it a more accurate data set to use for testing this. The answer is it's taking approximately 3 minutes, but the error bars are huge because there are algorithms we can turn on, algorithms we can turn off, and we've intentionally been careful to not do any premature optimization on this. But we are ready to start optimization. We also have GillPix projected coads and HIPS trees. This is something that's needed for the data management portal and for EPO, for example. These were used for DP 0.2, generated for DP 0.2, and I think they're definitely on the development instance, and I think are going to be ported over to the production instance of data.lsst.cloud this week or very soon. In DP 0.1, there were some single frame astrometry fit failures that were getting reported as successes, and there were a very small number of these, but it only takes one to ruin your COAD. So as a result of this, we have added stricter checks on the astrometric fits and more safeguards to prevent them from going into the COADs. Okay, next are some updates on algorithmic components. I'm going to go through the first 2 and then hand it off to Claire. Okay, so the first algorithmic component, there are actually 2, because the story of photometric calibration and background estimation have been intertwined for the past couple of years. To demonstrate that, the plot on the left, for public data release 2, Eli ran the photometric calibration code FGCM and binned up the residuals by position on detector. And they have this visible pattern. Now, the color bar it only goes from 2 millimags to negative 2 millimags. So the effect is very slight. However, whenever you see a coherent pattern in your residuals, you know that this is something that you can add to your model and fit for. This turns out to have been from the background estimation. On the right, to demonstrate this, HSC chips have 4 amps. Pretend one of those amps has a background of 100, the next 200, the next 300, the next 400. If you fit a 6th order Chebyshev polynomial to this, like we do during single frame processing, and subtract that off, you get a series of ramps that look exactly like those that we see in the photometric residuals. And if you're wondering, oh, but that your HSC backgrounds can't possibly look like that toy image on the right. I assure you they do. This is the binned backgrounds in G-band from HSC PDR2. So to account for this, we used an algorithm from Pan-STARRS called the pattern continuity algorithm. It was written by Chris Waters and implemented by Lee Kelvin. These images are from Lee. What it does is it forces the backgrounds at AMP boundaries to match. And the image on the left is the before, the one on the right is the one in the middle is the after. And this was turned on for PDR4, and we're looking forward to seeing how this improves photometric calibration in PDR4. But in general, for photometric calibration, a number of other updates have been made this year. We have been achieving 5 millimag uniformity and repeatability for a while now. This past year, we made some changes that make us more robust to reference star outliers, and better handle the changing filters. HSC, we swapped out the first I-band and R-band filter for another I-band and R-band filter because the first ones weren't performing as well as expected. Next steps are to further try to mitigate the effects of the backgrounds by looking at the measurements that we use for sources that we use for photometric calibration. Right now, we use top hats, 12 pixel radius circular apertures, and we are pursuing compensated aperture fluxes, or as Robert and Eli call them, compensated filter fluxes. So compensated filter fluxes are an idea from Robert, implemented by Nate, and validated by Eli. It's essentially a profile that goes negative in the wings in order to subtract off the local background. If you look at the performance of these compensated Gaussians, you'll see that on the faint end, there's increased signal to noise and better handling of the effects of the background. You don't see that same curve in the faint end that you do with the top hat apertures. Okay, just like last year, the active optics session was scheduled for the same time as the pipelines update, so I'll be speaking on behalf of Josh as well. Arun is attending virtually and is here to answer questions. For PSF estimation, this past year we have started using a repeatable, consistent set of stars for PSF modeling. That is, in every visit during single frame processing, we use the same set of stars for PSF modeling. We've also switched from PSFX to PIF by default. PIF stands for PSFs in the full focal plane, even though right now it does not actually model PSFs in the full focal plane. We've been using the pixel grid model for now. This uses pixel coordinates. We, during the commissioning phase, found that we had to tweak a couple config parameters, but are generally happy where we ended up. To validate that this was performing comparably to PSFX, these are some of the automatic plots that get generated during pipeline execution. It's the size of the star divided by the size of the PSF minus 1. For ideal perfect PSF models, this would be an average of 0 and a scatter of 0. And you see that the scatter is approximately the same. Next steps are to switch over to using sky coordinates instead of pixel coordinates, incorporating the camera distortion model. And of course, the main benefit of PIF is that it's in active development now. And so any new features that get added to PIF are automatically made available to the pipelines. The next algorithmic deep dive is astrometric calibration, and I'll hand it off to Claire, who's attending remotely.
Hi, I'm sorry I can't be there in person. So The current status of astrometric calibration is that we are continuing to use the joint cal package, and this is what's being used in our current pipeline and for the PDR2, or sorry, PDR4. But over the past year, we have added an improved outlier rejection algorithm, and this has really helped with, sorry, can you go back to the previous slide? This has really helped with yielding a much faster runtime. So the plot on the left is showing a little schematic of approximate runtimes per number of visits for the old and new versions, and you can see that we've gone down from on the order of weeks to a couple days for very large data sets for joint cal. So this really helps with our current status. And before I go on to the improvements that we're working on, I just wanted to remind you all that we are currently achieving the design specifications for astrometry. The plot on the right is showing the current AM1 metric, which is showing the RMS in milli-arc seconds between stellar pairs at a distance of 5 arc minutes. And for the RC2 data set, we are getting well within the design standards. But we know that there are ways to improve, so I'm going to talk about that in the next slide. Okay, so what we're currently working on is adding the GBDes package as an alternative to joint cal. So this is a C++ package for fitting astrometric solutions that was developed by Gary Bernstein for DES. And it has a few significant improvements over joint cal. It implements fitting of proper motions and parallax. It's significantly faster for large data sets because of some differences in the algorithms. And then also it can accommodate effects like tree rings and different adaptations for the mapping between pixels in the sky. So currently what has happened is we've done a significant refactoring of GBDes to make it more object-oriented and adaptable to wrapping in Python, and implemented a Python or a PyBind 11 wrapper and a build system for GBDes. And right now a pipeline task, just drop-in replacement for joint cal, is being added to the DRP pipeline. So the plot on the right is showing that with an equivalent model, we're getting basically identical results between GBDes and joint cal as expected. And then we're hoping to work up from this to more improvements. Okay, so next slide. Okay, so as I said, we're currently in the final stages of adding GBDes to the DRP pipeline. So the plan is to first establish a baseline performance, and then once we've done that, we can turn on proper motion fitting. So outside the scope of the actual pipeline, I've already tested GBDes' performance fitting proper motions, and so the plots here are showing the scatter in milli-arc seconds as a function of magnitude, and the plot on the left is showing results basically as they would be in the current pipeline. And then the plot on the right is showing the same data but with the proper motion fitted. And you can see that we get a significant improvement in the scatter with proper motions fitted. So this is something that we can do to take advantage of all of the data that we're getting from the Gaia catalog, which includes proper motions and parallax, and use that information to significantly improve our results. And this should be something that we can do quite quickly. Okay, so the next slide. So once we have that sort of lowest hanging fruit taken care of or implemented, some of the next things that we're looking at doing are accounting for atmospheric effects. So the plots here are showing residuals over the focal plane for one visit. The plot on the left is residuals in RA, on the right is DEC. And what you can see, especially in the declination plot on the right, is that there's this sort of wave pattern, and That's been argued to be a signature of atmospheric turbulence. So one of the things that we're looking at doing is implementing something like methods shown in Fortino 2020 and Leger 2021, where they used Gaussian processes to fit out atmospheric results. We haven't entirely decided how to do this, but this is something that other projects have shown good results on, so we're hoping to be able to do something similar here. And then next slide. And then another thing that we'll be working on is accounting for some of the subtler effects from camera geometry and the effects from individual detectors. So the plot on the left, it's still a little bit fuzzy, but here I'm showing what happens when you take a stack of residuals over many visits. And I've used a sort of simple model for fitting the astrometry here so you can see the camera geometry a little bit better. But basically you see sort of a ring or like circular pattern that's due to the camera geometry. And this is something that we could make a little bit more of an informed model about to get an improvement in the astrometry there. And then the plot on the right is from the Leger 2021 paper, where they showed that after stacking hundreds of visits, you can see these tree ring effects in the astrometric residuals for individual CCDs. So once we have accounted for some of the bigger causes of astrometric residuals, and we have enough data to process to see these things, which we can do with some of the larger data sets that Yusra was talking about, then we'll be able to look at getting down to some of these finer effects. So that's the current status of astrometric calibration.
Hello? Okay, there we go. Thanks, Claire. Okay, so I'm going to be talking about the deblender, kind of both current and potentially in the future. And so last year, so kind of between the release of DP 0.1 and 0.2, we switched from using the single band deblender to a multi-band deblender using Scarlet, which is a package that I developed with Peter Melchior at Princeton. And then, since then, it's kind of had a lot of other contributors. Remy Joseph was a postdoc who was helping out. I think, everybody on DM really kind of helps with everything in a lot of ways because we do code reviews and we give a lot of input to people. And I think it's good to recognize that. I think, kind of Jim Bosch and Yusra's role is often underappreciated because like every month we plan everything out that we're doing. And then there's also been a lot of, really good algorithmic and code reviews from Dan Taranu on this package. And then some, Nate Lust, whose name you see on like everything on here, because he like has his hands in everything. And, he helped design the persistence model that I'll talk about in just a minute. But I'm going to be talking in the deblending session tomorrow, so I won't go into too much detail about this. I'm sure you're probably going to be as sick of hearing me talk about this as I am. So I'll just, give the basic overview. Is what Scarlet does is it creates kind of a model across all bands in a partially deconvolved space. And then it convolves that in the observed seeing, compares that to the data, and then back propagates the residuals, and it does that in an iterative process. So it kind of starts out with a single deblender input, and then just iteratively updates it. And it was really designed to be a general deblending tool. And so Peter, for example, was concerned with joint processing of space and ground-based data. And so there's a lot of pieces to that framework that we don't really need for Rubin data. And so the last year has mostly just been kind of working on performance to try and improve that so that we can, both improve the memory usage and the runtime. In the end, we're going to use whatever deblender is working best that's shown to perform best on scale. So if you have something you've been working on and you think it's ready for that point, then let me know, and I'd be happy to, to start, kind of running it and see how it does, because, we want to make sure we're using the latest and greatest, whatever that is. So currently, what we've been developing in-house is Scarlet Light, which is basically Scarlet. So if you look at the upper left plot there, that's the Scarlet model for this particular blend. If you look at the top right, that's the Scarlet Light model. The bottom left is the Scarlet residuals, so the difference between the observation and the model, and the bottom right is the Scarlet Light residuals. And what you'll notice is the residuals are effectively the same, up to numerical precision. Right, so if you're wondering the difference between Scarlet Light, the algorithm is exactly the same. It's identical. The only difference is we've just taken a lot of that machinery out that was needed to do rotations and changing the pixel grids and everything between different cameras, because we don't need to worry about that because we're operating all on coads that have already been WCS aligned and they have the same pixel grid. We're also going to be producing metrics. So to try and give you some input as to whether or not we think this was a blend that was blended successfully. It's not going to be a set of flags, so we're not going to say this blend is good, this source is good, this source is bad. It's going to be more like, this is how much this was blended with something else. This is how much flux it has overlapping with other things, and maybe give some advice on some cuts that we find useful to try and cut things out. But we're not going to tell you, for your science, whether or not this is good. We're just going to try and provide you with some tools to help out. And so the other big piece that we did that Nate and I worked on was moving to a model where we were actually. Oh wait, yeah, that's the slide. Okay, moving to a model where we're storing a more compressed version of the data, because currently we were just we were acting like the single blended blender where we take the Scarlet models, we rewrite the flux. And then we just produce that in the footprints in the catalog. But then once we've done that, you've completely and totally lost the models that went into it. So now we're actually storing those models on disk. And, we've seen an order of magnitude drop in the size of what's being stored on the disk, and we also have access to those models now for users downstream. And just kind of showing the difference between Scarlet Light and Scarlet, we've essentially decreased the memory usage by 2 orders of magnitude, and the runtime by a factor of between 5 and 8. And so again, most of this year has just been to try and make it more performant, because for a long time it looked like we weren't sure whether or not we'd be able to run Scarlet at scale. And fortunately, it looks like with Scarlet Light now we can. Now I will pass off to.
Hi, so I am Ian Sullivan, manager of the alert protection team. I'll be first talking a bit about work that Zach Lanford, a very productive post-bac student who has been working with us for the past 2 years, was doing. He has now moved on to graduate school at UPenn and is busy with other things, but he did very helpful work for us. One of the things that was his major contribution was implementing trailed source measurements, which is now in the stack, and this is run on all of our DIA, difference imaging analysis objects. And he implemented several different flavors of this measurement, one a very accurate one based on the Varies model, and then a faster one based on adaptive moments that were already being calculated within other measurements in the stack. And he was able to make use of these adaptive moment measurements to get measurements that were essentially as accurate as the Varies model that is otherwise in literature, and with the exception of being about 10 times faster, which, given that we are going to be running this on many different objects, made this possible to have it run by default in the stack, and it's in there now. So if you are looking at source catalogs and there are trailed sources in there, you will have shape and length measurements. I should also point out that we also have source injection code. So, and I don't know if this will be in the source injection talk tomorrow, but with source injection, you can put in these trailed sources and test for yourself the accuracy of the length, flux, and other measurements of our trailed sources. I want to talk very briefly about something that was mentioned. I talked longer yesterday in the difference imaging analysis session, just to make sure everyone is aware that we have refactored our image differencing task to make it more robust, more testable, and more adaptable to to different styles of convolution or different imaging difference imaging algorithms. It is now broken down into conceptual steps of building the templates, doing the actual subtraction, so either an Alardon-Lupton style subtraction or potentially a Zogi style subtraction, and finally the detection and measurement of those on those image differences. So what is in there right now, and this is current in the stack, is this new set of tasks that will do the image differencing. What is in and well tested is the flavor that convolves the template using Alardon-Lupton. This is what most people have been using for many years. The one that is currently undergoing some verification and some bug fixes is Alardon-Lupton style, where you convolve the template, and in future but soon development would be pre-convolution of the science image to create a maximum likelihood image for source detection on the maximum likelihood image. One thing that I don't have on this list, but it is straightforward. We had it in the previous task before it was refactored, was that a Zogi implementation, and given different priorities and staffing, we may be able to implement that in the future. Just like to highlight some of the metrics. This is coming from around the time that we made these changes. We were trying to maintain compatibility, but in the metrics as we made this switch. Now that we have, and I'd like to highlight that the timing only changed very slightly. We're doing essentially the same algorithmic steps. Added up, it's about 5% faster, but not really enough to make a difference. And the differences in the source detection measurements have changed only marginally. These are going to be sources that were right at the very edge of detection thresholds. Now, this is our metrics we're showing here, a change of about 2 sources out of around 1,000. They will be changing more as we go forward and as of this week, because now that we have this new framework, we can start fixing some bugs that were present in the previous task. With that, hand it over to Nima.
Hey everybody. Yeah, my name is Nima. This is me, but I have to have my mask on. Just like what Ian said, I pretty much covered everything that I'm presenting here yesterday in the DFIM session. So if you were there, just feel free to not look or not listen. I'm a new member of the AP team since a few months ago. I kind of coordinate the learning-based or deep learning-based approaches and implementations. Let's talk a bit about the problem definition and the motivation. I need to talk pretty fast because things are very condensed here. So on the left, you see a 4K by 4K pixel image of one visit, and it's the motivation of what we are doing here. So like any other detection task, we are going to have ground truth, which are the green dots, and then detections, which are the blue dots. And again, like any other detection problem, there are misses or false negatives and false positives or false alarms. And we want to somehow tackle both these issues. So we are taking 2 approaches in parallel. One, the blue one, is we internally call the traditional real bogus classifier. And the one on the right is called TransInet. And as you see, its placement in the diagram is a bit different it is more independent of the difference imaging. And let's take a deeper look into the two methods here. So on the left is the binary classification or the Real Bogus classifier. On the right is the end-to-end implementation of TransInet. So that is the official thing so far on the left. And on the right, you can consider it more experimental in the sense that it is not yet integrated into the stack fully. However, it is not a new method. It's been there around since 2017. So the method on the left helps with purity only in the sense that it can detect the false alarms and try to reject them, but it doesn't have access to the things that are not detected or missed. We try to address that with TransInet. The one on the left, for it, the problem is defined in a way that the candidate is always at the center of the patch. And we have worked on it. We know that it is some sort of an ill-defined problem. Because, I mean, for starters, how would you define the center pixel of a 32 by 32 patch? These are even numbers, so there is no center. I mean, this is more like a joke, but yeah. So the one on the right does not need the TransInet or candidate to be at the center, and does not need it to be does not need the patch to contain only one candidate. And for near future, I am working on making TransInet to digest one single visit at once. So this is probably going to help the speed of the alert production process as a whole. So our current status. So the Real Bogus classifier is basically a simple binary classifier. So Arif, one of the students, has implemented one version based on DC2 data and one off-the-shelf binary classifier based on ResNet. And you see the results are pretty good here. Note that in the truth, we don't have the misses. So this is kind of an evaluation of purity compensation, let's call it. And this is also a balanced evaluation of the metrics in the sense that we have only a few hundreds of positives and thousands of negatives. So we should be careful about that. And this is the current status of TransInet. It is, as I said, pretty experimental in the sense that it is, I mean, just trained on DC2, it is still learning. But as you see, I mean, these dots that probably are not visible to you from farther are the detections, so the peaks of the heat map. So this addresses the purity and completeness in the sense that it tries to dig out the things that have been missed during difference imaging or image differencing. And this is a slide for Robert to initiate a discussion in the aftermath of this presentation. This is about the purity of one of the cutouts. And so I tried to increase the dynamic stretch of or decrease the dynamic stretch of the plot. And we see that nothing like an artifact or noise starts appearing there. It is too good, but yeah, we will discuss later. Oh, and where we are standing right now is to test everything with DC2 data. Where we are going is to try to make our models generalizable to the unseen data. So this is the Achilles heel of deep learning methods. You train them on the source domain. You never know how they are going to perform on the target domain. And these are the proposed approaches. And the last one is my favorite one. Thank you.
So this slide presents where we were with the asteroid linking problem last October. And I want to emphasize that this is all built on the foundation of Matt Holman's development of the HelioLink algorithm, which is a clever new way of linking asteroids. And Siegfried Egel, my predecessor at working on the asteroid linking for Rubin, elaborated the HelioLink algorithm significantly, implemented it successfully in Python, and demonstrated that it worked on LSST, simulated LSST data. So that was basically where it was when I joined the project. But last year in October, we couldn't test the HelioLink algorithm on all sky samples from LSST. It wasn't fast enough. It was demonstrated to work, but it wasn't fast enough to be tested all sky. So we did tests in small, limited regions of the sky, like the green and orange rectangles shown here. And there were also, although the completion was good, there were also issues with purity. A lot of mixed linkages existed where the two distinct real objects would be linked into a single candidate discovery. So what's new, or where are we now? First of all, again, building on Siegfried's excellent work, I've re-implemented the algorithm in C++, which makes it run a lot faster. And now for the first time, we can feed it full sky data sets for the LSST. So this is based on simulations of what we expect the LSST to detect over a 2-week period for all the observations spanning the whole sky. This involved elaborating the hypothesis space for HelioLink. So previously it was effectively a 2-term Taylor series in the heliocentric distance as a function of time. So a heliocentric distance at a specific reference time plus the radial velocity at that reference time. And I've added the second derivative of the radial velocity, second derivative of the heliocentric distance, first derivative of the radial velocity, which is not necessary in all cases, but it helps improve the purity and completeness. There's also post-processing that we now have in place that evaluates a whole bunch of overlapping candidate linkages generated by HelioLink itself, and of the set of candidate linkages that involve the same point. So you can imagine a big subset of linkages that are mutually overlapping. It identifies the best one using metrics that I've developed. And this is powerful for helping with purity. So it allows us to, in most cases, select the best of a set of overlapping clusters. So the result of all this is that we have 97% completeness or better on both main belt asteroids and near-Earth asteroids. It's even over 98% for main belt asteroids for realistic simulations of everything that LSST should detect in the solar system. And what these completeness numbers mean is they are fractions of the total number of objects that were potentially discoverable, where that is defined as 2 detections per night, a pair of detections separated by at least 5 and not more than 90 minutes on 3 distinct nights within a 2-week period. So that's the definition of discoverable, these 3 pairs of detections. And the separation has to be at least 5 minutes and not more than 90. Those parameters are, of course, flexible, but that's what we're working with right now. So if we compare that, is 97% good? Well, the specification is 95%. So by that definition, it's good. We're above spec. If we compare it to the state of the art, that's a tricky question because no existing asteroid survey is trying to do anything like this. They're all using 4 observations per night and not observation pairs. So I could say, well, the state of the art is 0, which of course would not be quite fair. But in any case, this is good performance going forward. And we have lots of ways to make it even better. So first of all, we haven't implemented orbit fitting, actual orbit determination yet. But there's strong indications that this is possible. It's possible to do it fast enough. And this will be another really quantum leap forward in terms of our ability to vet good clusters and produce a really pure sample. The current HelioLink implementation hasn't yet produced excellent results on trans-Neptunian objects because they move too slow. In many cases, the pairs of detections that we get are essentially on top of one another. You don't get any leverage to determine an angular velocity, which is essential for linking. But there's no reason that we can't just tune the parameters in HelioLink so that we're making effective pairs that span multiple nights for these really slow-moving objects. And also, the 2-week limit is extremely conservative for trans-Neptunian objects. We can probably link over 2 months and detect objects that were theoretically undetectable. In the interest of time, I'll sort of skip over the rare geometries. You can ask me about that later, but it's a problem we believe we have a good solution to, and is not a very serious problem even there. Finally, we need to integrate this well-tested C++ code with the LSST pipeline so that we can make use of all of the good information in terms of trail detections and trail length and orientation and other stuff that the LSST pipeline will provide.
Thank you, Ari. Okay, we've had a lot of talks this meeting. Most of them have already happened. Please go back and watch the videos if any of these topics interest you. To advertise some of them that are coming up, Merlin's giving a session on instrument signature removal later. Sophie, Lee, and Josh at source injection tomorrow, photometric calibration tomorrow, and more on deblending tomorrow. Just to echo something that Fred said, even though we've been putting the scientist who led each project at the bottom of the slide in order to highlight to you who is the best person to direct your questions, everybody has worked on everything. The Science Pipelines team is one team working on one code base, and we all own the one code base. Looking at the questions on Slack, I wanted to add one more thing to this list of more information. This year at this talk, we've been very careful to include only changes that have happened in this year since August 2021, the last PCW. So this talk was a delta on the PCW 2021 talk, which was a delta on the PCW 2020 talk, which was a delta on the algorithms workshop talk, which is the best place again to look at the plans. But also, if you want to hear more about any of those updates in previous years, the PCW talks the videos are also available for updates those years. And I will leave these resources up on the slide and hand it off to Robert to moderate our Q&A session.
It went green. This is amazing. I didn't see. Okay, let's go red again. Okay, so I didn't see many active questions on Slack. Maybe some are coming in. Are there any on Blue Jeans? Who was monitoring that, Melissa? Okay. Okay, so we've answered all the questions. So I guess we're going to have to open it up to the floor, or else we can go and get an early lunch. So any questions either on the new material presented here, or as Yusra says, on the other things that you might be interested in because you haven't come to all these sessions on previous meetings. So we should be able to answer any question about the science pipelines. Ian?
Okay, got it, great. I was going to bring up Tim's question from Slack. Tim was asking, are we going to include the Lattice survey data in our data holdings, including catalogs, such as making it available in DP1? Robert, you had some comments on that. Yeah. But
well, I can answer the boring part of that, which is that data automatically flowed from the mountain to NCSA in the old days, soon to USDF. We're talking with Colin at the moment about automated processing of that. And the pipeline, all the code you saw produced was with LSST code. So everything we take with Auxtel will be fully processed. So it would be a policy decision, and will just slipped out as to whether we want to put that into QServe and whether it's worth doing. There's no reason why we shouldn't. The data set is not very deep. It's a 7-minute field on a 1.2 meter telescope. So whether it's really something that's going to add to the Rubin legacy, I don't know. Do you have any thoughts about whether we would want to do that, Yusra?
Yeah, I would say Oxtel's main value now is that it is online when before ComCam goes on Sky. And once we have data from ComCam, the survey from Lattice will become a lot less interesting.
And in fact, at that point, the Oxtel will go back to doing spectroscopy to try to understand the absorption in the atmosphere. And that data will be released with the regular data processing. So I think if nobody here is really pressing for this survey, there's a good chance that we won't release it with DP0 unless there are political reasons. But there's we don't care.
So online, Tim is responding that he does care about making that public, and so he is pushing back.
Okay. Well, I suggest that Tim talks to Will, and we figure out whether we want to do that. I don't. Is there anything? There's no further input from this room. I think we'll let them talk to each other offline. Yeah. Okay. Question over there. Either find a mic or.
Yeah, I would like to hear more about the Gaussian compensation on the wings and the calibration. Is that something that's only in the calibration step, or now photometry will have different profiles for the PSF? I think I would like to hear more.
Finally. Okay. So the compensated Gaussian filters are really only suitable for stars. It doesn't make sense to do. So for galaxy photometry, we have these Gaussian adaptive aperture HAP colors, which uses the PSF models, but these compensated filters are only appropriate for stars. And at the moment, we are only planning on using them, for the photometric and, astrometric calibration kind of second order, because to get, select signal above some signal to noise. But the advantage is that it'll take care of any local background offsets, so we can be a lot more careless with the background and kind of sidestep some issues and still get the best photometric calibration as early as possible. And then we can actually do a better job with the background if we actually know the actual throughput and all of that. But once there's still some work to be done there that we have not.
Jeff Carlin here, or one of the local group people? Yeah, Jeff, do you want to say something about whether you're interested in using this for local group in the presence of nebulosity and bad backgrounds and things like that for doing photometry?
Yeah, put me on the spot.
I can answer the question for you.
Totally fine. No, I think one of the concerns for things like in the local volume where you're looking at point sources on top of unresolved emission, the photometry is difficult, if not horribly bad, usually. So I think if that's something that could conceivably improve the photometry in situations like that, I think that would be excellent.
Did you want to?
No, I think that's great.
I can ask the boring question, which is, are we actually measuring these fluxes on everything in the catalog? Are we running?
No. At the moment, we aren't running it at all. It's still in development. So no. But I have run and the I have run it on everything in the RC2 run, but where it will be run is even earlier than that. But no, it'll have to be run on everything in the single frame processing in order for us to get down to the signal to noise that we need. So everything in single frame will have this flux measurement. Yeah, and we will. And now that I think it through, it will be run, and it's super fast. Thanks to Nate, wrote it. So.
But it does sound as if we could run it on the curve. Well, I think there are cases that if you're only interested in point sources, this is an interesting way of doing the. Jeff.
Just to add to that, I guess you could imagine then pushing your detection threshold a little bit lower, since you'll be able to actually extract a measurement in places of elevated background. And if we're setting a 5 sigma limit or whatever it is we use, and you may want to do that iteratively or something, but for cases like with elevated background, it would be interesting to test that.
We have talked about exploring that at the detection phase, using that as the detection filter.
Yeah, that sounds great.
As early.
Okay, we probably should move on. Fascinating. I love the topic, but did you want to say something? No. Okay. Other questions from this side of the room? Come along. Somebody over here must know something interesting to ask about. We'll pick on Salman next. Otherwise, yes, you said you had a second question. Okay. Do we have anything online, Meredith? Oh, no, Melissa. It was Melissa doing it, right? Yeah. 0. Okay. Yusra, did you have any backup topics you wanted to explore if we fail to extract questions from the room?
Nobody has any questions here? You can pepper us. This is the first time we've all been in the same room at the same time in years. So.
Okay. Yeah. Finally, 2 questions. Okay. Sedaghat, you're first.
Just a quick one. So for HSC PDR4, is the sky subtraction the same as for PDR3?
Okay. And could people hear that question?
I can repeat if you want.
Well, the question is, for HSC PDR4, is the sky subtraction the same as HSC PDR3? And I believe the answer is yes. But Yusra should.
Yusra is probably the person to answer
that. The main difference is the continuity, the amp-to-amp matching pattern continuity algorithm that we showed earlier that matches the amp boundaries to be continuous across the boundary. That's the primary difference to backgrounds between PDR3 and PDR4. Other than that, everything is exactly the same.
Okay, thank you.
Here. I have a question about Real Bogus, and specifically about quantifying model confidence.
Would you hold your mic a little, or we can repeat the question?
Sure. Can you hear me better now?
Okay.
Okay.
In that case, why don't you say it and I'll repeat it?
Sure.
Say it and I'll repeat the question.
Sure. So my question was about Real Bogus and about quantifying model uncertainty and when to and if to retrain the model periodically during the survey. And both in terms of like how representative the current incoming data for the alerts is to the training set, and also just for ranking.
Nima, did you get that question?
Yeah, I'm trying to get this on. It's on. Okay.
Can you repeat the question as you understood it and then answer it?
Good point. Yeah. So your question was, in simple terms, when we update the model. Yeah. So as I showed in the last slide, it will be retraining itself over its lifetime, but of course with a slower pace. So we will get a feedback from the output, how it is performing, and always feed it back to the training process. And there are several ways. So for starters, I mean, for the very first visits, what we are going to do is to be prepared for whatever that comes. But then we are also hoping to get some labels, some annotations for the new data as we get it, from citizen science to active learning, and use the metrics from there to update our training. And it will be like a closed loop which is connected forever.
Anyone else? Yes. Maybe it's best either Ian or Eric probably wants to take that question. Yeah. Mike's closer to you.
I think the answer is no. They're not. They're distinct. At least in alert production, there is an association to the DRP object table to the nearby objects. I'm going to look to Yusra if I'm forgetting something about DRP, but they are distinct. And are we providing some convenience cross match in DRP? I don't think we are. There's no association at all. Yeah.
No association. Associating sources is not the optimal way to get objects or DIA objects, and for that reason, we are using other methods for determining DIA objects and objects. Okay, so the DIA sources are aggregated into DIA objects, and then the centroids of the DIA objects are force photometered on the difference images and the CalExps. So you will have the measurements on the CalExp, the single frame total. I think we call those tote fluxes in the DIA source or DIA source table. Yeah, so there are other ways to get at those total fluxes on the single epoch images that are not from the detections and measurements on the single epoch images.
Any other questions? Well, I will use. Oh, yes, there's another question. Nate, we've got Jim online. I mean, we could start out by saying how many data sets we have run this pipeline on, I guess. I mean, well, I mean, before I hand this off to Yusra or Nate, I mean, I got our code running on ZTF at some point, and that was a nightmare because of the way that the overscans are stored in extra HUs, and you can't get the bias frames and all that sort of stuff. They just don't exist. But it wasn't very hard to get the code up. It took me a few days. So, I mean, we have got this running on multiple cameras. So, I don't think it's the butler is the limit. It's data formats and weirdnesses about different cameras. Looks as if Ian was interested in answering the question. Oh, I'm sorry. Yeah. So the question was.
Test this mic again. I think it got muted. It is now green.
Okay.
Claire, can you hear me?
Okay, good. So the question was how hard it was to get this code running on a new data set. And I claimed that it really wasn't very hard, and I've made it run on lots of data sets, including ZTF, which was kind of a challenge. However, Eric wants to answer that question.
I just want to point out that Robert, you might not be a representative user from the community, so bear that in mind.
Eric wants to say that if I can do it, anybody can do it.
The main thing is that we don't make it easy to use master calibrations that somebody else has produced. We really want to control, I mean, we have pipelines for producing master calibrations, but we do not, we want you to, everything works better if you use those to make your own master calibrations from the raw calibrations. And it's not as easy as like, I'm going to down these calibrations from the telescope website and use them. It's just, that's a lot harder. But of course, making your own calibrations for our system is fairly difficult too. It's not something, frankly, I would recommend for like, I took a couple of nights of data with a telescope that no one's processed, through our pipelines before. But if you've got your own little mini survey, then it may be worth the time investment.
Jim said, that was Jim Bosch, who was sitting in Princeton. He said, one of the difficulties is that we don't make it particularly easy to take calibrations that you've generated externally and apply them. We kind of expect that you'll start from the raw bias flat frames and do everything consistently. And it's not worth it if you've got 2 nights, but if you've got a survey, then it's certainly reasonably straightforward. Jim didn't say straightforward. It's worth doing it, I think, what he said. Okay, well, let's close. I'm just going to make one, because I'm the moderator, I get to make one comment, which is the reason why Yusra was showing you these amp-to-amp issues is because they're in the hardware on the HSC camera. So we were working around hardware problems on a camera. It's interesting that solved that. I see you, Melissa. We're going to have corresponding problems on the big camera. And one reason we put that much work in was to say, we can handle camera problems. We've learned how to do it. The next time we give this talk in 2 years' time will probably be, we found these horrible things in the A to Ds on the LSST cam, and this is how we worked around that. So that was kind of the motivation at some level, as well as getting science out of HSC. Melissa, you have a question.
So a question from the Blue Jeans. This is from Raul. He says, we heard some new interesting methods on transient detections from Nima. If these would be thought to be good, what time frame would it take to obtain sufficient training data? And what would be important for capturing sufficient variations / diversity in images? Would that be air mass, PSFs, etc.? So it sounds like a question for Nima.
Yes. Thank you. And now I need to see the question again. Transient even if this would be, what time frame would it take to obtain sufficient training data? What would be important for capturing sufficient variation diversity in images? Would that be air mass, PSFs? We already have some trained model on DC2 data, and the training from scratch could take anything from 1 week to a month or even more. But we are not going to start from scratch from now on. So we have a model and we keep fine-tuning it on the new data. So that is I would say in 1 day, probably during the daytimes, we can fine-tune the model to the new data as it comes. The time frame for having TransInet integrated into the stack itself, I'm looking at something like 3 months or so. And so regarding the PSF and air mass and other things, the difference between the two methods is that one is discriminative, the other one is generative. So here the generative model, okay, cautiously generative, because that has a precise definition in data science. But anyhow, the transient method would be robust to new artifacts because it has learned how to focus on regenerating the transient, not focusing on discriminating out the artifacts and noise. And that's why it should be pretty agile in adapting to the new configurations.
Thank you. Okay. Yeah.
Robert.
The end.
It's a follow-up question from Rahul. Maybe if you could see it from Ian as well. He just says, so do I understand that you'll be happy to use DC2 as a training sample and you don't need LSST data?
No. So DC2 data is too artificial, let's call it. I mean, even if you plot the histogram of images, you see that you have a pretty beautiful Gaussian for the noise model. So we definitely need to adapt the model to the new domain as the data starts coming to us. So, I mean, I can guarantee that it will fail if we train it only on DC2.
I suspect we should probably take this discussion offline. Did you? Yeah.
Come today, Lauren is offering party favors.
Shiny, colorful stickers. Sorry to those who are virtual.
Okay, well, we better not waste any more time in that case before we hand over our colorful stickers. So thank you for everybody who presented. Thank you for coming. We're all here. We're happy to answer questions. And next time we see you, we'll have ComCam data. It'll all be different. Thanks.